The presentations are for the invited talks, and the first two presentations will be invited talks are 20 plus 5 minutes, and then for the contributed talks we have 15 but plus 3 minutes. I will remind all speakers when there are 5 minutes left, just with the idea is that we keep some time left for questions. Yesterday there was quite some interesting discussion, also the day before. So hopefully this will be also in the last day of the future experiments and future facility session. Yesterday in the morning we had up to 42 participants. So far we are only 11. I hope that far more will join in the next few minutes, but just in the sake of getting started in time, Markus, I would like to ask you to start with your talk on an update on upgrades by LHeC, and then let's hope that in the next 1 or 2 slides of your presentations there will be far more in the discussion. So thank you.
Thanks a lot, and thanks a lot for the organizers for giving me the opportunity to present the plans or the current process of upgrading the LHC experiment for LHC Run 3, and also for giving you an outlook to the future. For LHC Run 3 will provide new opportunities for LHC, but it will also come with new challenges. It will give us the opportunity to answer questions with more precision, which are still left open, like, for example, the thermalization of heavy partons in the QGP, or the precise measurement of germania. And here I'm also talking about excited states as probe of deconfinement, and precision measurement of the low mass dileptons as a sign of chiral symmetry restoration, measurement of thermal photons in order to assess the initial state of the QGP, and also to assess the initial temperature, the QGP, for doing detailed studies of jet substructure or hard-on-jet correlations for photonic for the study of photonic energy loss in the medium, and for searches for bound states involving strange quarks. Those will be all possible thanks to the increase of the interaction rate we expect for Run 3 with a lead at 50 kilohertz interaction rate. However, this will also have new challenges for LHC. In order to collect the full rate, we will have to improve on our readout in order to be able to collect the full rate. Therefore, we have to improve the readout rate in order to, in particular, separate certain certain probes, the pointing resolution and the PT resolution, particularly at low PT. Would profit from improvement also for the measurements of displaced vertices, and in particular the data rate to tape needs to be significantly reduced with an increase of roughly 50 kilohertz, of roughly 50 times the interaction rate. But at the same time, the current performance, for example, the particle identification capability, should be preserved. Therefore, the LHC experiment is doing several updates. The current inner tracking system will be replaced with a new inner tracking system. The readout of the TPC will be upgraded based on so-called gem stacks. In forward direction, where we are measuring the muons, we'll get a new tracking system which extrapolates the muons in direction to the primary vertex. The experiment will be upgraded with a new interaction trigger called fast interaction trigger. Plus, several detectors will get upgrades in the front-out readout in order to cope with higher rates. In In addition to the detector upgrades, also the computing system will be upgraded with a new online data processing system, which will be capable for doing reconstruction steps in the process of the data taking. The new inner tracking system, which is replacing the current inner tracking system, will be based on the so-called Alpine chip, which is using monolithic active pixel sensor technology. It will have a thickness of 50 microns with a granularity of 2000 pixels per square centimeter. It will consist of 7 layers in two modules, three layers in the so-called inner barrel, which is close to the interaction point, and 4 layers in the outer barrel. In total, the inner tracking system consists of roughly 24,000 chips, leading to 12.5 gigapixel. The distance to the collision point in the inner layer will move from what we have at the moment. It's at 35 millimeter to 25 millimeter. In addition, the radiation length in the inner barrel will be reduced to 0.35% of the interaction length, and the readout rate will be increased to 100 kilohertz LED and 400 kilohertz PP, so certainly enough for the 1-3 conditions. With these updates, we can see that we can improve our tracking efficiency to approximately 90% still for tracks with PT around 200 MeV over C, and we see an improvement in the pointing resolution to the primary vertex with respect to the current ITS by more than factor 2 with the new layout. The TPC will be upgraded by in the readout with so-called gem stacks. The main motivation here is to be able to go to continuous readout. With the current setup, we have a significant ion backflow into our drift field, which we currently absorb something called a gating grid, which has to be closed once the event is read out to absorb the ions from the drift field. But this also limits our rate we can operate the TPC with. In order to improve on this, we are using for run 3 a readout based on gem stacks, replacing the multivariate proportional chamber, which consists of a 4-layer gem stack. The main advantage is that the avalanche is dominantly created in the gem hole, for which the dominant part of the ions drifting back are directly absorbed on the gem stack. With this, the ion backflow is reduced to less than 1%, which means that the need for the gating grid, which was there in run 1 and 2, is no longer there. So the TPC can be operated at high readout rates. As you can see on the right side, the performance is similar to the performance we had in run 2. We see that the momentum resolution for TPC and combined tracks is roughly the same as what we had in run 2 with the MVPC readout, and we see that also the DDX resolution, which is used for the particle identification, approximately stays the same. In order to operate the TPC in a continuous mode, we also need to replace our front-end electronics. with a new chip called Sampa, which is doing the preamplification and shaping. It's based on CMOS technology with 32 channels per chip. Still staying with a 10-bit ADC. This allows the digitization at 5 megahertz, which is crucial for our continuous readout. In order to extrapolate muon tracks to the primary vertex, we have a new detector called muon forward telescope. This detector is using the same technology as our new NR tracking system. It's using the Alpine chips. It consists of 5 layers, each having 2 disks, one upper disk and one lower disk, with in total 920 chips. It covers the acceptance from -2.45 to -3.6 in unit rapidity, approximately matching the rapidity of our muon tracking, muon identification system. And its main purpose is to propagate muons to the primary vertex. This is of relevance for 2 things. First of all, it's of general interest for measurements of muons, like in particular for low mass dimuons, but also precise tracking of muon tracks to the vertex allows the separation of muons from secondary vertices. That's of relevance for detecting muons from heavy flavor decays, in particular the separation of muons from B hadron decays, but also for muons for non-prompt shape psi measurements in the forward direction. And we see that with this new system, we have a matching efficiency for muon tracks with our muon tracking system, which is larger than 90% for muon tracks with PT larger than 90 with muons larger 2 GeV, and in the same PT region, we have a pointing resolution of 30 microns. Our trigger system is replacing our new trigger system is replacing our old trigger system with a detector design which is actually very similar. So the trigger system, fast interaction trigger, consists of 3 detectors. The FIT V0 detector, which is a scintillator, replacing our old V0 detector. The FIT T0 detector, which is a Cherenkov detector, replacing our old T0 detector, and the diffractive detector, a scintillator detector, is replacing our old diffractive trigger. Its main purpose here is to be a fast interaction, a fast collision trigger, which flags the minimum bias events with a latency of less than 425 nanoseconds. The T0 detector is also used in order to provide a precise measurement of the collision time for a time of flight detector, which is used in, for particle identification based on a time of flight measurement, for which a precise measurement of the collision time is necessary. And in addition, it fulfills an tasks which were also then run too. It's our luminosity monitor, but it also measures the event centrality in heavy ion collision and the event plane. And as you can see on the right side in the plot, the performance with the new trigger system shown here for the centrality determination is the same as the performance we had in run 2. So in order to reduce the data volume, we recall that we have 50 kilohertz light collisions. This would result in several hundred petabytes per year data if we would not compress our data and only store the raw data. That's certainly not feasible. So significant compression is needed, at least a factor 100. In addition, as we run in the TPC in a continuous mode, we'll have multiple collisions overlapping in the TPC drift time, which need to be separated, which needs some rethink, some adaptation of the reconstruction. For this, Alice is commissioning new online-offline computing system where the reconstruction is included in the data taking process. It consists of, in the online level, the online reconstruction consists of 2 levels. The first level is called first level processors. Those are directly connected via the readout cards to our detectors. They receive the data and they're preparing them for the further processing. And then they are shipped to the event processing nodes, which have roughly 2,000 GPUs in addition to this, the CPUs, which is the main workhorse for the event reconstruction. With this, we achieve, as you can see, we reduce from approximately 1.1 terabyte per second at raw level from the detector to roughly 90 gigabyte per second to tape. So we get the expected factor 100 in reduction of data rate.
Markus, you have 5 more minutes.
Yeah. In addition, we'll also have some online calibration and data monitoring in the online process. The installation process started last year with the TPC installation in August, October, and later fall we had a mini frame installation, and in winter the MFT and FIT installation. And this year we're we started also the installation of the inner tracking system, and the first collisions at 900 GeV are expected this summer. In the meantime, we're also testing we're commissioning on testing our online and offline computing system, with the online commissioning has already started last year, and this year preparing for a big simulation and analysis challenge in summer. And here you see a couple of pictures from the various installations. In the upper part, the TPC installation, then next the mini frame installation in late fall, and the installation of the MFT, FIT, and in the barrel detectors. As you see for the physics performance, we expect that with the new detector we will be sensitive to address possible rope broadening, and we will be able to also separate prompt and non-prompt chip size in forward direction, and we will get a strong improvement in the D-meson impact parameter, in the D-meson pointing to the primary vertex, which is important to measure beauty via non-prompt D-mesons. In addition, there will be also the possibility to make precise measurement of the D-meson fragmentation and the measurement of jump variance. In addition to the heavy flavor program, Alice is also working on a PP program with an integrated luminosity of 200 inverse picobarn at an interaction rate of 500 kilohertz, where we use an online event selection on DPN to select interesting event candidates. Some highlights for this is a measurement of particle production at very high multiplicity events. There also to study possible collective effects in small systems at very high multiplicities. and the precision measurement of the dead cone effect by comparing BTAC jets to DTAC jets. Giving a short outline, short update outlook to run 4. Sorry, there is a plan to further upgrade our inner tracking system by replacing the 3 inner layers, so the inner barrel tracking with new fully cylindrical detectors, which again reduces the material budget. It's closer to the collision vertex, which allows us even further improvement, factor 2 improvement of the pointing resolution at the primary vertex, which can lead to up to factor 4 increase in the significance for the charm variance in that lead collisions. Furthermore, a new detector will be introduced to measure photons at very forward direction. The main goal here is to put stronger constraints on the gluon nuclear PDFs, which, as you can see, have at small x and low q square sizable uncertainties. And the main observables which are sensitive to those are direct photons from the gluon quantum scattering and heavy flavor from gluon fusion process. As you can see, if we go to very low x, we have a stronger sensitivity by direct photons. But in order to measure those, we need an isolation cut in order to enhance the fraction from quark gluons scattering with respect to photons from fragmentation processes. For this, Alice is introducing a new detector called FOCAL. It's at 3.2 to 5.8 units of rapidity in forward direction. It has some complementarity to LHCb, which is measuring the heavy flavor process. However, it can go to slightly even lower x and q square. It consists of 2 colorimeters, an electromagnetic sampling colorimeter and a conventional hadronic colorimeter. The electromagnetic colorimeter is designed as from two systems, one with low granularity, consists of 16 layers, but one with one silicon system based on the Alpine chip with high granularity, and this will allow us shower tracking. On the lower part of the right side, you see the prototypes for both the full PET, the full silicon PET colorimeter, the full PET colorimeter in the tests on the test beam at the SPS. But also it was tested in the in-beam direction next to the Alice detector in the 2018-13 TV data, and on the left side there you see the high granularity part tested at the test beam at DZ. And with this, having together the hadronic and the electronic colorimeter, will have good photon isolation measurement, enhancing the signal from direct photons. And you see the measurement of the isolated photons will put significant constraints on the gluon nuclear PDF with respect to the current with the current PDF sets. And for run 4, Alice is proposing a completely new detector, mainly focusing on tracking and particle identification at very low PT, down to a few tenths of MeV, in order to have few precision measurements of charm variance in excited charmonium states in heavy ion collisions, but also and also for low mass dielectrons, for example, and many more. It will only consist of a tracking system based on silicon silicon tracking, a time of flight system for particle and for hadron identification, and either shower pixel calorimeter or rich detector at barrel and end cap for electron identification. With this, I come to the summary. Alice received some major upgrades of its detectors for Run 3, in particular for the ITS, the TPC, the MFT, and the FIT detector. We upgraded our data processing scheme in order to handle the increased data volume, and those improvements will allow us to make new probes accessible in Run 3, which were inaccessible in Run 2. And for Run 4, we expect we are planning even further upgrades for the inner tracking system, and we are preparing a new detector, a new calorimeter at forward direction, in order to constrain some nuclear PDFs that's more at very low X. And for Run 5, we're designing completely new experiments, in particular for multi-charm variants or dielectrons at very low PT. Thanks.
Thank you very much, Markus, for the detailed updates for Alice Run 3, 4, and 5. This was really interesting, but unfortunately, we are really now also over time. I see there is one question. Dave, is it, let's have one short question and one short answer, and then go to the next talk. Dave, please.
Okay, nice talk, Markus. In the current silicon upgrade, the inner barrel is supported by a service cone, which gives you a way to route the services out one side. In your description of a future experiment with a really hermetic silicon coverage, are there strategies for routing the signals and other services out that don't compromise the very, very nice reduction in the material budget?
Oh, the way how the service structure is planned for the new experiment for Run 5, I must admit I'm not an expert on.
I expect that'll be very challenging.
Yeah.
Okay, thank you.
Thank you very much again, Markus. This was really very informative. Thank you very much. We now stay at LHC, but go to one of the other LHC experiments, CMS, where we will hear an update also then for high luminosity LHC. The speaker is Conor Henderson. I'm looking forward to your presentation, and I will give you a 5-minute warning.
Okay, very good. Thank you very much, everyone. And so, yeah, I'm very happy to be here. I hope you can see my slides okay. Once I go into full screen mode, Zoom sort of hides a little bit, but trust everything is fine. And I will be presenting here some future physics prospects with CMS at the high luminosity LHC. So we'll start with a little bit of a short introduction to the idea of high luminosity LHC and the planned CMS detector upgrades, but most of the talk is going to focus on the potential physics reach. So we'll take a look at projections across the range of physics that we hope to do with CMS, starting with heavy ions, talking about the Higgs sector, some precision standard model measurements in the top quark sector, and then finally concluding with some sense of what we might be able to do with beyond standard model searches. So just give us the context, the high luminosity LHC, the collision energy is expected to increase to 14 TeV, and concurrent with that, we expect to increase the instantaneous luminosity by a factor of about 4 to 5. And of course, that'll result in a significant increase in the integrated luminosity over time. And for most of the projections shown in this talk, we're considering a benchmark scenario of an integrated luminosity of 3,000 inverse femtoborns collected in about 10 years of operation. And so for comparison, in Run 2, we collected about 150 inverse femtoborn of PP collisions. So to cope with the challenging operating conditions in this high instantaneous luminosity environment, the CMS detector is planning a significant set of upgrades for HL-LHC operations. And I just kind of summarize it on this one slide here, but each of the different components has its own references to technical proposals or technical design reports that you can go to and look up for more information. Just some of the highlights in terms of triggering. We will be able to include the tracking output in the level 1 trigger for the first time, which would be very exciting. The end-cap calorimeter is going to be upgraded into a high granularity calorimeter with a large component using silicon as the active material. There'll also be upgrades to the tracker, to the barrel calorimeters, to the muon systems, and the beam monitoring systems. And also there'll be addition of a new timing detector to give precision timing capabilities as part of our particle identification. All right, there are many publicly available results where we've tried to do a projection as to what physics reach or sensitivity we might have for various situations with CMS at the HL-LHC and the upgraded detector. I'll just be given a sort of short overview of some of them here today, but there are many, many more. And if you're interested to read others, then they're all available at the link that's posted here. And the other thing I'll just point out is that each of our analyses has this unique sort of identifying analysis code that you'll see then spread out through the slides and the rest of this talk. And if you want to read more about them, you can use that to identify the specific accompanying documentation. So let's start with a discussion of heavy ions from HL-LHC. The plan is to have both lead-lead and proton-lead collisions at two different nucleon center of mass energies, 5.5 and 8.8 TeV. Several different projections for heavy ion physics capabilities have been done. I'm just going to discuss two here. The first will be jet quenching, and then the ability to constrain nuclear PDFs. So in the dense, strongly interactive medium produced in the heavy ion collisions, the partons undergo significant energy loss, and that leads to the phenomenon of jet quenching. Now, to study the mechanism for that energy loss in more detail, one wants to do more precision measurements and, for example, measure the energy density even within a jet as a function of the distance from the jet central axis, and that's what's shown here as or. And in particular here, what we're looking at is the ratio of the density of particles produced as a function of this radius parameter or in lead-lead collisions relative to the same measure in proton-proton collisions. All right, so this measures the suppression effect or the modification of the jet properties in the strongly interacting medium in the heavy ion collisions. And so what we project in performing this measurement at high luminosity LHC is a really significant reduction in the uncertainty of these measurements as a function of R. So what we're seeing here in gray is a measurement, an existing measurement with its existing uncertainties. And you can see the large uncertainty at these outer radial measurements. The projected uncertainty then for doing this with heavy ions at high luminosity LHC will shrink that uncertainty by a factor of roughly 3 or so. And so we'll have much more precise experimental data that'll help us shed light on the details of this parton energy loss in the medium produced. We also expect with heavy ion collisions that we'll be able to constrain the nuclear PDFs much more strongly. An example of that is shown here. So by looking at the photoproduction, in this case of upsilon 1s mesons, that is basically related to the gluon PDF. And with the data that's available at high luminosity LHC, we'll be able to then, by measuring this photoproduction, we'll be able to constrain the gluon PDF over a much expanded Bjorken axe range compared to what has been available up till this point. So these are projections here that should take it to 10 to the minus 3, pushing 10 to the minus 4 in axe So this will be some significant constraints then on the gluon PDF from these measurements. All right, so we're covering a whole range of physics. So we're moving on now from heavy ion physics to talk about Higgs physics. Of course, this is a crucial sector to explore at high luminosity LHC. And in fact, there's actually going to be a dedicated talk about Higgs at high luminosity LHC by my colleague Corinne Mills. That's going to cover both CMS and ATLAS in the plenary session tomorrow. So I encourage you to see that for more details. I'm just going to focus on two components of this overall Higgs program. So one will be studying the Higgs coupling strength across the various decay channels that we have access to. And then the second is to look at di-Higgs production as a way to directly probe the Higgs potential. So in terms of Higgs coupling sensitivity, of course, the key here is that once the standard model Higgs mass is known, basically every other parameter is fixed. And so that means there's a clear prediction for what the standard model Higgs coupling to each of its different decay or production modes is. And so what we want to do is measure that as precisely as possible, and perhaps, you know, maybe we see some deviation from the standard model prediction that might indicate that it's not just the standard model Higgs. So for high luminosity LHC, we have these projections shown here, which are based on basically extrapolating the Run 2 results into what we think we can do with 3000 inverse femtobarns at HL-LHC. So first of all, in blue is showing the statistical uncertainty in each of these modes. So this is the coupling to photons, W and Z bosons, bottom quark, taus, and then finally the much rarer coupling to muons. This is expressed in terms of the coupling strength. So basically, this is now then a relative uncertainty on this compared to what the standard model prediction would be. And so you can see in blue from the statistical uncertainty alone, it should be at the level of 1 to 2% for the majority of these channels, a little bit higher for this very rare muon channel, but still within 10%. And then in terms of systematic uncertainties, two different scenarios are considered. One is basically propagating the Run 2 systematics, which are obviously larger. And then there's this labeled YR18, which was the yellow report from 2018, which is trying to project what we think we might be capable of doing for systematic uncertainties in these measurements with the HL-LHC data set. And so if we're able to achieve that, then the total uncertainty would be shown here in red. And so you can see that what we're potentially looking at is uncertainties, you know, on the order of about 5% on these more precision channels, even less than 10% for BB bar, for example, and less than 10% for dimuons. And so you can see that we're getting to a point where we can really constrain these couplings extremely well, and it'll be a very important test of the standard model Higgs to see if they do indeed agree with the prediction. One can do the same thing. These are for decay modes. One can do the same thing for the various different production modes, gluon fusion, vector boson fusion, associated production, etc. And we can see then we also have a pretty strong ability to constrain those as well with HL-LHC. And if you want to see more details in this, as I said, the results can be found in this particular public result from that web page that I mentioned earlier. All right, so that's studying the Higgs coupling to individual channels. One thing that's extremely interesting to look at is the Higgs coupling to itself. So basically, in the standard model Higgs, the potential is completely fixed, as shown here. It's the famous negative mass squared term, and then this lambda parameter that represents the self-coupling. But of course, the standard model is basically the minimal way in which you can create a Higgs field to solve the problem of electroweak symmetry breaking. Doesn't mean that that's the way that it is actually implemented in nature. Now, the only free parameter basically was the Higgs mass. The ratio of these couplings give you the vacuum expectation value, which comes into so many observables that it's extremely well constrained. But basically, once you've measured the mass as well, you now can you now sort of have access to the full value of both parameters. But the question is, well, what if it's not a standard model potential? Are there other contributions, or could it be, different, right? And so do we have a way to probe the Higgs self-coupling directly? And we can try to observe di-Higgs production. Now, there is a contribution to di-Higgs production from the Higgs self-coupling from diagrams, for example, like this. And so if we can observe this, we have a chance to probe directly to self-coupling and see what the actual Higgs potential is. Now, this is a very challenging measurement. It's a rare process. I show an illustration here from a Run 2 result looking for di-Higgs, where one Higgs decays to bottom pairs, the other Higgs to diphotons. These are the mass distributions for the diphoton and the dijet mass here. And then in red is the expected standard model contribution multiplied by a factor of 100. So you can see that it would be very challenging to see this. And in fact, from the Run 2 search for this, the limit is more than 20 times the standard model. So that's as sensitive as we're able to get. So CMS has done a projection as to how sensitive we might be to this important measurement in high luminosity LHC with 3000 inverse femtoborn. So this is based on a combination of channels, the all Bs, combinations of Bs and taus and also Bs with various dibosons, photons, Zs, and W. And we can see putting those 5 channels together, we maybe can reach 2.6 sigma is the expected significance for this with the combination of all channels for this benchmark luminosity scenario. So not quite at observation threshold or evidence threshold, but starting to push into that territory. Another way we can look at the same thing is in terms of how much we could use those studies to constrain the coupling modifier. So relative to the standard model, that can be expressed as a modifier kappa lambda. Basically, when it has a value of 1, then the coupling is equal to the standard model coupling. And so you can be sensitive to a range of different kappa values. And this is the likelihood scan here shown for each of the different channels. The narrower the curve here, the more sensitive the individual channel. And then black shows the combination of all of them. And so if we can, the likelihood value here corresponds to 95% confidence level along the gray line. And so basically we could expect with this combination of channels to exclude everything outside of the intersection of the black line with the gray dash line. And so that means that we should expect to constrain this coupling modifier to the range here of about slightly less than 0 on one side and slightly less than 4 on the other. So it'll be a pretty narrow constraint for this important probe of the Higgs actual potential. And indeed, as I mentioned, there are many other Higgs results, and so I'll encourage you to follow the dedicated talk that I mentioned in the plenary session on this. All right, so moving on from the Higgs sector, we also have the possibility of doing this kind of precision standard model measurements and at HL-LHC. And here I'll talk a little bit about top quark measurements. And I look at just 2 of the available things. One will be studies of the differential cross section, and another will be the search for the rare production of 4 top quarks in a single event. And so what we show here is a projection of what we might be able to do for differential cross-section measurements of TT bar production. On the left as a function of the transverse momentum of the top quark, on the right as a function of the rapidity. And we can then compare these to the theory predictions as an important test of the theory. And you can see that the expected uncertainty here is basically less than 5% across almost all the entire rapidity range, and from the majority of the momentum, transverse momentum range as well. So it allows us to really do a very high precision correlation study between what's observed experimentally and what's predicted for this standard model process. In terms of 5
more minutes.
Okay, thank you. In terms of where those reduced uncertainties come from, that's shown in this slide. So there are various sources to the combined systematic uncertainty from the jet energy scale, from the B tagging uncertainties, and so on. There's also theoretical uncertainty is actually a pretty important one at the highest transverse momentum. And so the dashed lines show the uncertainties that come from the current Run 2 results, and then the solid line, same quantity that we project the uncertainty to be in HL-LHC. And so you can see there's roughly a factor of 2 improvement in what we expect the uncertainties to be. Another important measurement or observation in the top sector will be the search for four-top production. It's a rare standard model process, and it can also be sensitive to a variety of beyond standard model scenarios that would enhance this production. So this is being searched for at run 2, and taking those results, we've done a projection of what we might be able to do with 3000 inverse femtoborns at HL-LHC. And so as a function of the integrated luminosity, if the only uncertainty was statistical uncertainty, we would reach 5 sigma observation within a few hundred inverse femtoborn, including these projected systematic uncertainties. Obviously, that's going to slow down our ability to observe it, but we project that with 3000 inverse femtoborns, we should be at around the 4 sigma significance, so exceeding the observation or the evidence for level, I meant to say, and pushing for observation. Alternatively, another way that we can say that is that if we constrain the potential cross-section for this process, we should be constraining it in the region of about 20 to 30% uncertainty at that point. All right, so I'll move on to my last section, which is to talk a little bit about beyond standard model searches. So we've looked at some standard model measurements. Now we can look at what we might be able to do in terms of direct searches for beyond standard model processes. Of course, there are many scenarios here. I'm only showing a couple of them here today to give you some flavor. The first will be a dark matter search, and then 2 searches for heavy resonances in different channels. One way that one can look at dark matter at the high luminosity LHC is in the production, first of all, of mediator particle. Here, some example of a Z prime produced in association with the Z boson, which then decays the dileptons, and that's basically what we observe in the event. Z prime then decays to a pair of dark matter candidates, which are invisible and leave no signature in the detector. So we get the events containing a Z boson plus missing transverse energy from the escaping dark matter particles. And what we project with the HL-LHC is to really be able to reach extremely large values of this missing transverse momentum in this channel. Then in terms of distinguishing potential signal from the background here, we can express this in terms of what we think the discovery significance might be. So using some of the standard dark matter models, we have basically fixing most of the dark matter couplings. Basically what your sensitivity is really thought of then is the sensitivity to this mediator particle that couples standard model on one side to the dark matter on the other. And so as a function then of the mass of the mediator, this is what our expected significance for observation is as a function of the integrated luminosity. And so once you get above the gray line, then you've exceeded the discovery threshold. And so with 3000 inverse femtoborns, we should be able to discover mediators if they're in the range up to about 1 TeV. Beyond that, it'll be hard to claim discovery. And then alternatively, if you want to think of it as exclusion limit, that is shown on the right-hand side. And then the last 2 things that I'll talk about real quick were some searches for heavy resonances. So here we'll talk about some heavy scalar particles. So an example could be like a heavy Higgs partner, a Higgs-like particle at a much, much higher mass, decaying to 2 Z bosons. And in this case, we look at the Z going to one Z to dilepton and the other to dijet. Where we consider cases where both the jets are separately resolved and where they're merged together and using substructure techniques. So this is based on extrapolating the 2016 Run 2 result. And what we see is shown on this slide. So the projection for the sensitivity in terms of the cross-section for this production process that we can exclude is shown here on the left. And for comparison, the 2016 result on the right. I'll just point out that the axis label is different here. This is a cross-section from Run 2 in picoborn. This is a cross-section in femtoborn. And so there's a significant increase in the sensitivity of cross-sections for a process like this that comes with the higher collision energy and the higher luminosity at HL-LHC. And for more details, you can read the individual talk. All right, and I hope I'm just in time to come to my last search, which is a search for resonant production of top quark pairs. And that's something we'll have access to with a large luminosity and collision energy. And just skipping to the sensitivity of this, if we look here on the right, in terms of 3 sigma evidence or 5 sigma observation for example of a resonance that could produce a TT bar pair, in this case, the Randall-Sundrum gluon, excited state of the gluon, you can see that we could push the evidence / observation thresholds to around 6 TeV with 300,000 inverse femtobarns at high luminosity LHC. So significantly really increasing the range of in which we can explore new physics scenarios. All right, so that brings me to my summary. Thanks for listening to the talk. I hope you've seen that we can cover a wide range of physics processes with CMS at HL-LHC, from heavy ions through Higgs, precision standard models such as TT bar, differential cross sections, and then of course a whole range of beyond standard model scenarios. And for the full set of projected results, I refer you to the CMS webpage. Thank you.
Thank you very much, Conor. This was really a good overview about all the physics prospects at CMS. I really enjoyed your talk. We have time for maybe 1 or 2 questions. Are there any questions for Conor?
Yeah, Daniel here. Hi, I have a question to the standard model expectations. Do you have prospects for other standard model parameters like sine square theta, W mass, and alpha S?
Of those ones, I know that we certainly have ones that are looking at electroweak sector physics. I don't specifically know, but I will maybe check the list of things on your behalf a little bit, and I'll maybe post it in the chat window if that's okay. If there are some specific ones so that relate to that, I'll do a quick search for you.
Yeah, perfect. Thanks.
All right, no problem.
I have a quick question for you. So on your slide 4, you covered the detector updates which you will do for high luminosity LHC. Which one of those would you say are the really essential ones to allow new discovery?
Well, there are going to be several, of course, but I think the couple of ones that I find very interesting are upgrading the NCAP calorimeter to the high granularity ability. That'll be very important for sort of studying some of these more, forward measurements, and then we can get good constraints on so a lot of the forward physics there. I think also for a lot of exotic scenarios, particularly you're thinking about like some of these long-lived things for which maybe the detector was not originally well designed. I think one of the things that'll be exciting will be including tracks at the level 1 trigger, which we have not been able to do to this point. So that will allow for far more precise triggering on a lot of these exotic scenarios involving tracking. So I think that one will be a very interesting one too. And I'm sure there are other significant increases that can come from the combination of all of these upgrades, but those are probably the 2 that I would think are maybe the most significant.
Thank you very much, Conor. So let's go to the next presentation. We already had a few presentations on LHeC, and today we will hear about LHeC as part of the high luminosity LHC program. Ludovica Aperio Bella will present.
Hi, can you hear me?
Yes, need your slides, and then I give you a 5-minute warning when you reach the 15 minutes mark. Perfect.
Please, let me know. This is not full screen, I guess.
Yes, it's large, but not full screen.
And here should be full screen.
Yes.
Okay, and I will stop sharing my face just because of bandwidth sickness. Okay, so let me know if there is some problems on the sharing thing.
Okay.
Okay, so thank you very much for giving me the opportunity to present indeed the LHeC physics program as a part of high luminosity LHC program. So let me start introducing where do we stand now and the duality of the current and the future particle physics program. So right now there are bunches of very well-known open questions of the standard model, and the goal of the LHC and future experiment physics program is indeed to find an answer to those questions. But the real paradigm of the current time is where to look for deviation of standard model, and there are two separate and very distinct approaches that can be pursued. So the first one is look for direct search of new sign of new physics, scanning, for example, planes of couplings versus mass of new physics, like in the example on the left on the slide, or indeed looking for very precise measurements of fundamental electroweak parameter in standard model, which can indeed help us to give us an hint of where the new physics can hide. Of course, LHC is both, so energy frontier, a high precision machine. And with this talk, I'm trying to convince you that the concurrent EP and PP operation can really achieve the ideal potential to answer to these questions. Okay, let's go to next slide. So next slide, I will just quickly flash the high luminosity LHC plan since the previous talk, and I hope that you are quite familiar in this. So even though the extraordinary results obtained with the LHC Run 2 that is just finished, there are several milestone analyses which will reach full potential only with the high luminosity phase, in which we are going in a bit less than a decade, have an extensive upgrade of acceleration complex and all the detectors and run.
The slides are frozen. We still see the front page, page 1.
Oh no, sorry for this. So I don't know how to do this. Can you see now, David?
Just don't go to full screen.
I don't go to full screen.
Usually it's a problem with that.
If the problem continues, I would be also more than happy to share the slides on your behalf, and you just say me next slide.
Sure. Can you see now? This is slide 3.
We are still in your full screen mode, and we are still at the title slide.
Oh no, how I do this? Stop sharing. Can you see now slide 3?
No.
No.
Oh, okay. Let me.
Would you mind, in the sake of time, if I share on your behalf?
Absolutely. Sorry. Sure.
No. Just trying to help.
Absolutely. Okay, it's not those slides. It's not those one.
Wait, I'm so sorry. So
no problem. I'm now not anymore in full screen for Zoom. Can I try to share now, or you
please try while
I can't because you are sharing. If you stop sharing, I can try now, and you can see what you see.
Bear with me shortly. Okay.
Okay. So can you see slide 3 now?
Yes.
Yes.
Good. So I will continue like this if it's not a problem.
No, it's not. Please continue.
Okay. So can you see slide 4?
Yes.
Okay, good. So let me jump immediately on the LHeC basic concept. Just because I assume a lot of you know the high luminosity LHC plan already. The LHEC machine is a new next generation TV energy electron-proton collider, which can be extended as an electron-ion collider, which will extend the kinematic range by 3 order or 4 order of magnitude with respect to the previous kind of this experiment like this. And with its 3.3 TeV center of mass energy, the LHeC would provide a major extension of the disk kinematic ranges, which is required for energy program at energy frontier, like the high luminosity LHC. The accelerator complex is based on L machine technology, which is quite smart. And the LHeC may operate synchronously with the high luminosity LHC and collect 1 or 2 inverse autoburn after the final data taking at high luminosity LHC area, which is one of the main takeaway message here. And I also please give a hint, a look on the previous talk that were done if you want to particularly details on this on the technical aspects of the LHeC. So in this talk, I'm going to focus more on the LHeC physics program, and in particular, not on the very own standalone physics program of LHC, but mostly on the complementarity of the high LHeC physics on the high luminosity LHC, and in particular, trying to convince you that this 3 beams twin collider can give us, can make the high luminosity LHC complex as a much more powerful laboratory for searches and measurements, covering a full and spanning a full ranges of measurement from BSM, top, Higgs, precisions, and even nonlinear QCD in the very small axis. So let's start with the core of the program of LHeC, which is of course the Barton distribution function resolution. And as you already knew from Claire talk of yesterday, the LHeC provide a single coherent based information of PDF determination up to M3LO. And this will span reduction of uncertainty for gluon, luminosity, and PDFs, and also for all the valence and the quarks PDFs. And here, just 2 examples here. And in the next slides, I'm trying to convince you that this is an essential input for fully exploitation of current and future hadron colliders measurements, because the knowledge of PDFs has important impact on all Higgs, BSM, electroweak, and whatever physics program that you have in proton-proton collision that often are limited by the PDF knowledge. So let's start on the high luminosity LHC and the LHeC complementarity in the constraining of the PDF uncertainty. So in these slides, you will see the prospect of how pseudo data from high luminosity LHC in blue and in red then can shrink the uncertainty of the current best knowledge of PDF for LHC 15, which is the best sets, which contain fits for a lot of data, also not only from Hera and Tevatron, but also for LHC. And you can see that really the combination of both data will will give us a significant reduction of PDF uncertainty over a very wide range of axes. And but you can also see how the LHeC is the correct and really necessary input to complement the DPP colliders, because can really reduce the uncertainty on PDF in regions where LHC cannot really reach. So another very important natural role of the EP experiment is to highlight the QCD insights. And as you probably also already seen in several other talks that were given, not only LHC physics can give us alpha strong measurements at per mil level, but can also access to novel kinematic ranges of this, characterized by very, very, very small x values, which has indeed some impact so first of all, it's very interesting by per se this region, because there the standard collinear perturbative description based on the gap evolution cannot work, but also because this low X region can have impact on observable that are very important for high luminosity LHC physics and beyond. As I can show in these slides, 10, where in the plot you have the comparison of the ratio to N3LO cross-section for the Higgs. And you can see the effect of the small x resummation on the cross-section versus the square root of S. And you can see that this effect can be seen already at high luminosity LHC, in the High-Luminosity LHC measurements, but it is even more important when you grow in energy. So here is a very important aspect where LHeC have an unprecedented kinematic reach to explore small x phenomena. Another very important aspect of the high luminosity LHC physics per se, so standalone physics program, is of course the electroweak and top physics. And here I just highlight some measurements that can be potentially done with the HL-LHC data. So first of all, the anomalous WTB couplings, which will be very complementary with something that you can do at high luminosity LHC, and of course the precision measurements of W mass in the T channel or the running of the sine squared theta. But for more details, please, you have dedicated talk tomorrow, actually, on this subject. But what I would really like to show today is how the LHeC input are really essential for the extraction of this K parameter in proton-proton collisions. So as you probably know, one of the goals of high luminosity LHC physics is indeed to test consistency electroweak sector in standard model through the precision measurements to complement our, if you want, the direct search for new physics, because as we said, this indirect determination of a fundamental parameter of standard model can help us to reveal sign of new physics. And the W mass and the Weak's mixing angle are one of the two of the important fundamental of patameter, which are much more precisely determined with indirect determination, so with the global fit than with the direct measurements. And in the table in the bottom, you can see that the current knowledge of these quantities, so the measurements that are done at LHC currently, are nice, but quite far away from the goal of the threshold that are posted by the indirect determination, and those measurements are dominated by the PDF knowledge.
You have 5 more minutes.
Yes. So here I will show you quickly the prospects of the Weak's mixing angle analysis at high luminosity LHC made by CMS and LHCb. And you can see that even though the LHC experiments enter in precision electroweak rays using very new analytic techniques to reduce, for example, profiling the PDFs stay the major uncertainty and limiting uncertainty for the high luminosity LHC measurements, and therefore to reach really and to exceed lab precision and have an uncertainty on this fundamental quality, which is very, very compatible, you really need the input of LHeC. And the same, so shown here in red, and the same can hold for the W mass. So this is the prospect measurements for W mass measurements with low mu data in Atlas with the Atlas Upgrade detector, and you can see that PDF are really dominating at certain point while you collect enough luminosity with the low mu. And what really can ping down the uncertainty on the PDF on the W mass up to 2 MeV is indeed the input of LHeC program. Another very important point that I would like to stress is, of course, the Higgs, because with this new EP energy frontier, you can also have an Higgs factory with LHC is E alone. And here you can see the kappa, in the kappa framework that was also explained in the previous talk, what is the reachable sensitivity. But probably more interesting is to look at how these LHC results can be complementary with respect to the high luminosity LHC prospect in blue. And you can see that in several channels, the complementarity is extremely visible. And in particular, LHeC will give us the direct charm couplings that are not reachable to high luminosity LHC. And this is competitive and complementary even to the E plus E minus collider. So a few words about BSM. So LHC can probe also sensitive region for space-based, difficult to access for LHC for BSM physics. And but in particular here in slide 19, I would like to stress how the improvement of the knowledge of the large X gluon, the large X gluon and quark PDF can help in increase the sensitivity of direct physics searches, looking at this plot for SUSY and W prime, where the uncertainty on PDF on the signal is one of the main uncertainty. Last word before I'm going to the conclusion is about the unique and the revolution that can be exploited with this kind of facility. So the electron nuclear scattering and physics program. And in my last slide, I just want to flash how the LHeC data will allow direct measurements of LED PDF. And the particular extension of low axis ranges and the particular precision of determination of a nuclear PDF in these ranges can really help disentangle small X dynamics from nuclear effect and give fundamental input on QCD and shadowing and anti-shadowing of the quark-gluon plasma that is a very hot topic of on the heavy ion physics program right now. And I let my conclusion slides because I know that I'm already late. Thank you very much.
Thank you very much. And this has been a really great talk, despite this unfortunate technical problems at the beginning.
I'm sorry for this.
And when we subtract that, you even were perfectly on time. So so thank you. Are there any urgent questions for Ludovica? What would you say are the current prospects for the timeline for LHeC with respect to high luminosity LHC?
So
Maybe.
This is a very good question, and probably I was very quick there because of problems of sharing the slides. But one point that is very important to stress is that we expect LHeC to operate synchronously with the high luminosity LHC. So we expect the two experiments to operate, even though they are living in the same complex, we can expect taking data simultaneously for those two experiments. So this is a very key aspect of this new idea of new detector and new facilities.
Thank you very much. Given the time, let's go to the next talk, which will be by Alessandra Betti on prospects for Higgs and di-Higgs measurements at the ATLAS experiment.
Hi, hello everybody. So I'm going to try to share my slides. Can you see the slides?
Yes, not yet full screen, but it would work.
Okay, can you also see the slides changing?
Yes.
Just to be sure. Okay, so
yes.
Maybe we'll stay like this just to avoid problems. That's okay.
Yeah, of course.
Okay, so we'll start then. So I will present the prospects for Higgs and di-Higgs measurements at the ATLAS experiment on behalf of the ATLAS collaboration. And let me start with a very brief introduction explaining why we are interested in the prospects for Higgs physics. This is because we know that in the standard model, all the properties of the Higgs boson are defined once we measure the value of its mass. But we also know that this model is leaving many open questions, and we have many different alternative theories which are making different predictions for the properties of the Higgs boson and even for more than one Higgs bosons. So this is why after the Higgs boson discovery, we have started a large program of measurements of its properties, and this program is still currently ongoing using the LHC Run 2 data. And more precise measurements in the Higgs sectors are a very high priority in the future program of particle physics in order to try to probe the compatibility of the measured values of the Higgs boson properties to the standard model predictions. So we expect that with an increased precision, we might be able to observe even little deviations from the standard model expectation that would be then a hint of possible new physics beyond the standard model theory. So let's see where we are now. So we are currently finalizing the ADRAS Higgs analysis using the LHC Run 2 data, and we are also, of course, preparing for the new Run 3 analysis. And from the current published Higgs combinations, which are currently using up to the full Run 2 data set, depending on the channels, we have observed the GGF, BBF, BH, and TTH production modes of the Higgs boson. We have observed also the decays of the Higgs boson in BB, WW, tau tau, ZZ, and gamma gamma, and all the measurements that we have so far are in agreement with the standard model predictions. And we have between 10 and 20% precision on the different Higgs production modes cross sections. And for the Higgs couplings, we have about 5% uncertainty on the Higgs to vector boson couplings, and between 10 and 15% uncertainty on the Higgs to third generation fermion couplings. We are also finalizing the double Higgs analysis with using the LHC Run 2 data, and from the current published double Higgs combination, which are using only a partial Run 2 dataset, which is corresponding to 36 inverse femtoborn of data, we have 95% confidence level upper limit on the di-Higgs signal strength of 6.9, combining 6 different channels. And the Higgs self-coupling modifier kappa lambda is constrained to be between -5 and 12 at 95% confidence level from the combination of 3 channels. So as I mentioned before, we are now finalizing the analysis with Run 2 data, and we are preparing for the new Run 3 analysis, but we also know that we have the start of the High-Luminosity LHC, which is planned for 2027. And here we will run at the LHC nominal energy of 14 TeV, and we plan to have between 5 and 7.5 times the nominal luminosity, and we expect to collect about 3,000 inverse femtoborn of integrated luminosity, which will be about a factor 20 more than what we have now. So given this, we can say that the High-Luminosity LHC will be a sort of Higgs factory that will produce close to about 200 millions of Higgs bosons. So for this reason, this very large data set that will be collected at the High-Luminosity LHC will be used to measure the Higgs boson properties in details using both the single Higgs and double Higgs processes. We also know that, of course, the High-Luminosity Run will be a very challenging collision environment, and we will have completely new operation conditions for our detectors, given that we will have an increased instantaneous luminosity by up to a factor 4 compared to Run 3, and we will reach a mean value of about 200 interactions per bunch crossing. So for this reason, in order to be able to maximize the physics outcome of this run, we need to be able to maintain or improve the object reconstruction efficiency and resolution, and also to reduce the fake rates even in an environment with even more pile-up jets. For this reason, we have the phase 2 upgrade of the ADRAS detector, which is planned before the start of the High-Luminosity Run. And this will include an upgrade of the readout electronics, a replacement of some of the detectors with most recent technologies, also an extension of the angular coverage to the forward region, and an upgrade of the trigger and data acquisition system in order to be able to sustain the higher rates. So given all this information, we have done studies which are based on the current Higgs and double Higgs analysis that were performed using LHC Run 2 data. And these studies have been carried out to understand the expected precision and limitations that this measurement will have at the High-Luminosity LHC. So these are, as I mentioned, projections based on the LHC Run 2 data analysis. And these are made by extrapolating the latest published results. In particular, the projections that I'm going to show here today were performed between 2018 and 2019. So these were using the results that were available by then, using a partial Run 2 dataset. So the general strategy for these projections is to use these early Run 2 data analysis, which are using data corresponding to 36 inverse femtobarn or to 80 inverse femtobarn, depending on the analysis. Then these are scaled to the 3000 inverse femtobarn, which are expected at the High-Luminosity LHC. And also the signal and background cross sections are scaled to the ones expected at center of mass energy of 14 TeV. And then we need to make some assumptions when we make these projections. In particular, we assume that the upgraded detector performance will be able to compensate the pile-up degradation. We also assume that the theoretical systematic uncertainties will be reduced by a factor 2. And we neglect the uncertainties which are due to the available statistics of the Monte Carlo simulations, mainly because we are not able to have a good estimation of how many Monte Carlo events we'll be able to simulate in 2027. And then for the systematic uncertainties which are driven by the intrinsic detector limitations, these are generally left unchanged. And in some cases, these are revised according to detailed simulation studies of the upgraded detector. So let's start having a look at the extrapolation from the ATLAS Run 2 Higgs couplings analysis. These are using 36 inverse femtobarn of data for the WW, Z gamma, TTH, and tau tau analysis, and 80 inverse femtobarn of data for the gamma gamma, ZZ, and VH with Higgs to BB and Higgs to mu mu. These extrapolations were made using two different uncertainties scenarios. First one, which is a conservative scenario, which is using the systematic uncertainties based on the current Run 2 uncertainties. And then there is a second scenario, which is an ultimate scenario based on the estimations of the ultimate performance for the experimental uncertainties. And also here, the reduction of 1/2 is applied for the theoretical uncertainties. The results for these, the expected results for these projections are presented on the global signal strength, on the production modes cross-sections of the Higgs, on the Higgs branching ratios, and on the Higgs coupling parameters in the kappa framework. So let's start having a look at the global signal strength. Expected results, as you can see here, we expect that we will be able to reach a precision of a few percent, and this will be dominated by the systematic uncertainties. And one interesting thing to point out here is that, as you see here, there is an important impact of the theoretical uncertainties on signal, which is expected. So this will have a large will give a large contribution to the total uncertainty expected here. Then for the Higgs production mode cross-sections, as you can see here in the two different systematic scenarios that were considered, in both cases we expect to be able to reach a few percent precision on all the production modes cross-sections, and all these will be dominated by the systematic uncertainties. Then for the Higgs branching ratios, again, in the two different systematic scenarios, you see that also here we expect to be able to reach a few percent precision on the branching ratios. And most of them will be dominated by the systematic uncertainties, with the exception of the branching ratios to mu mu and Z gamma, where you see that we will be able to reach between 15 and 25% precision. And this will be still dominated by the statistical uncertainties. For the Higgs couplings parameters in the kappa framework, also here we expect to reach a few percent precisions on the couplings. Again, most of them dominated by systematic uncertainties, with the exception of the couplings to mu and to Z gamma, where we expect a about 10% precision, still dominated by the statistical uncertainties. We also have extrapolation from the ATLAS-RAN2 Higgs differential cross-section analysis, and these are using the Higgs to gamma-gamma and Higgs to ZZ to for leptons decay channels. Here, the expected results are presented on 4 different observables: the transverse momentum of the Higgs rapidity, the number of jets, and the transverse momentum of the leading jet. And these extrapolations are based on the analysis, which is using 36 inverse femtobarn of data, with one exception, which is the PTH observable in the Higgs to 4 leptons decay channel, where the measurement based on 80 inverse femtobarn is used. And also here we have the extrapolation performed using the 2 different uncertainties scenarios, so the one with the current systematics and the one with the reduced ultimate uncertainties. And here you can see in this plot an example for the PTH observable, which is interesting because this is giving sensitivity to new physics, in particular in the low PTH regime for the couplings to C and B quarks, and in the high PTH regime for new physics at large scale. Here we see that the expected results in the low medium PTH regime are a precision of about 5%, and for the large PTH regime we expect a precision of about 8%, which will be still dominated by the statistical uncertainties. Then we also have projections for the ATLAS-RAN2 double Higgs analysis, and these are using 3 different decay channels of the di-Higgs system: the 4B, BB tau tau, and BB gamma gamma decay channels. In particular, the 4B and BB tau tau projections are made from extrapolations of the analysis which were performed using 36 inverse femtobarn of LHC Run2 data, and then the BB gamma gamma projection is then actually made using a dedicated new analysis, which was performed using simulations at 14 TeV. Here, for the double Higgs projections, the results are presented on the expected significance for the di-Higgs signal, and also as an exclusion limit on the Higgs self-coupling modifier kappa lambda. So from the combination of these 3 decay channels, we expect to have a significance for the standard model di-Higgs signal of 3 sigma. So this means that we'll be able to claim evidence for this rare process. And we have an expected precision on mu of about 40%, and this will be still dominated for this process by the statistical uncertainties. Then about the constraints on the Higgs self-coupling modifier kappa lambda, we expect again from the combination of these 3 decay channels to be able to constrain kappa lambda between -0.4 and 7.3 and 95% confidence level, assuming that kappa lambda is equal to 1, as you can see here in the likelihood scan. So from the current projections that I just presented, which were based on analysis using still a partial Run2 dataset, we can already see that the High-Luminosity will provide a very great opportunity for the Higgs precision measurements. So we expect to be able to reach a few % precision for the Higgs couplings, and also we expect that the new rare processes will become accessible with the possible observation of Higgs to mu mu and Higgs to Z gamma, and also we expect that the rare Higgs production will also become accessible at the High-Luminosity. One thing that we should keep in mind here is that this is not really the full story, because we are already seeing with the new results using the full Run2 dataset that are coming out now, that we have improvements that are going really beyond the increase of luminosity. So we will expect that possible updated projections based on the new analysis will be certainly even more optimistic. And also we expect to have major progress in the future on improving the performance and also on reducing systematic uncertainties, both for the experimental uncertainties and the theoretical uncertainties, and also on improving the analysis techniques. So thank you.
Thank you very much, Alessandra. There is a question. Please go ahead, Max.
Alessandra, thank you very much. Hello, everybody. If you put the biggest optimism together, so we take all the improvements we are already seeing, we add CMS, and we run at 4 to 4 inverse autobahn instead of 3. Do you think we have a chance to see the self-coupling?
So if we do have already a combination of the ADRAS and CMS projections for the di-Higgs, and if I remember correctly, there from the projections that were made using this partial data set, we had something like, I think, 4 point something sigma. So it's not far from the 5 sigma, and so I believe that with the new analysis that where we see that there is a huge improvement, I believe that this will be possible.
I meant the self-coupling, not the di-Higgs.
Okay, so for the self-coupling itself, what do you mean exactly by like be able to see the self-coupling? So yes, so we will have for sure a reduced uncertainty on this, but it's so this will be a measurement. Once we start observing di-Higgs, which we should be able to do, then we can do a measurement of kappa lambda. Yes.
Thank you.
Thank you again, Alessandra, and thank you for the interesting question. So let's come now to the last talk of the session. This will be a presentation on the upcoming Electron-Ion Collider facility, where Krzysztof Piotrzkowski will talk about extreme photon interactions, precise luminosity measurement, and photoproduction tagging.
Okay, hello everyone. I can share now, right?
Yeah, please go ahead.
Can you see it?
Yes.
Okay, very well. So I will talk about extreme photon interactions at the Electron-Ion Collider at Brookhaven, which is now being designed. It will be a very versatile new tool for high energy physics with 2 interaction points. And the main subject for my presentation is the Bremsstrahlung process, which is on one hand very unique, on the other hand will be pretty relevant for making physics, good physics at the EIC. I will close with some remarks also about tagging photoproduction. So what is so special about Bremsstrahlung at high energy? To give you already a little bit of feeling, I distorted this diagram to stress the fact that this is extremely long range process. And what is very then special about it is that this range increases with energies of colliding particles. So it is not only that, it is also kinematics, which is very special. It is related to that, which is that the energy in the upper vertex is to very high degree conserved. So the sum of the emitted photon energy and the scattered electron energy is to very high degree equal to the beam energy. On the other hand, linked to this very long range property are the very small angles involved here, which are of the order of the 1 over Lorentz factor of the electron beam. So what happens there is for this process is that actually there is a proper solution that it is allowed, kinematically speaking, that all scattering angles are exactly 0. And this is where we find the minimum for momentum transfer, which is given by this formula using the variables in the laboratory system. And here you see that this minimal momentum transfer it decreases with the radiated photon energy and also with increasing beam energies. So what is also obvious, this is a scattering process, that this is this full momentum transfer is space-like, and it means that if one goes to the proton rest frame for some values of beam energies at the HL-LHC, what gets the minimal longitudinal momentum transfer, which is less even than 1 milli electronvolt over C. And it also immediately demonstrates this statement here that the energy in the upper vertex is well conserved, because the recoil of the proton in this proton rest frame is extremely small. If you take this longitudinal momentum transfer, you get this incredible value for the energy transfer. So now one can then interpret this extremely small longitudinal momentum transfer to the distance over which the interaction takes place, which is of the order of 0.3 millimeter for these HL-LHC energies. This translates then how to the impact parameter, to the of the colliding particles. Since the differential cross section is proportional to the Q2 -4 due to the photon propagator, basically, it means that if we integrate over the scattering angles and we discuss the Bremsstrahlung spectrum, it is dominated by transverse momentum transfers very close to zero. I mean, very small. It can be even zero, as I said, but typical ones will be because of this damping via this factor here, will be of the order of this minimal for momentum transfer over C. And this is the source of the beam size effect, which has been observed at HERA for low photon energies, because if one takes the HERA beam energies and calculates this typical impact parameters, one gets even more than 1 millimeter, which is much bigger than the typical lateral beam sizes, and that affects somehow introduces this effect of the Bremsstrahlung cross-section correction via this definition of a cross-section, which we all know very well, which gives the event rate of a process by multiplying the process cross-section by a certain number, which we call luminosity, which is defined, which is given by the parameters of the colliding beams. The problem with this definition is, which is a proper definition, but it assumes that the colliding particles can be well described by plane waves. And this assumption actually is broken for the Bremsstrahlung process due to the very large range of interactions, and at the same time relatively small lateral beam sizes. And this HERA observation was reported already in 1995. First, it was shown on the left here that one can very well describe electron gas Bremsstrahlung without any suppression present in low energies, whereas for electron proton, one sees this type of the effect if one divide the measurement over the prediction in squares here. What you see is the relative difference, the difference between prediction and measurement over the prediction. One sees that for E-gas, it is all close to zero, whereas for this black triangles, one sees that for a couple of GV energies, there is a suppression, which is well described by these circles here, which are the calculation of this effect provided a few years earlier. So the agreement was at the level of 30%, and one should maybe comment here is that the method used here assumed, actually, experimental method, that at high energies everything is described by leading order calculations, but the Heitel formula. So everything was normalized by construction to zero, so to say, relative difference here. So this is my remark that this particular measurement could not test this effect really at higher energies with high precision. So it was done with the luminosity detector of the Zeus collaboration at HERA, which is a little bit ironic here, because the Bremsstrahlung is a process which basically only one process, a relevant process, which breaks this luminosity formula at certain level, but nevertheless it was used because it has so unique properties that measurement only of photons was enough. So there was no need, it was found, to measure the scattered electrons to make this measurement, the luminosity measurement. So the achieved accuracy at HERA-1 was of 1%, with the cross-section uncertainty not completely negligible, or the order of 0.5%. Here you see the corresponding normalization or calibration distribution spectrum from those measurements. The situation at HERA-2,
we have 5 more minutes.
It was much, sorry, but I started 3:30. I'm only 10 minutes in my time.
Yeah, and you have 15 minutes.
And then for questions, okay.
Yeah.
So at HERA-2, it was much more difficult because of the synchrotron radiation problem in particular. Of course, the luminosity was also higher. It was the purpose of the accelerator upgrade, after all. But this very hard synchrotron radiation made the original measurement very difficult. So Zeus decided to go for the complementary measurement with using the converted photons at the exit windows. And then 22%, even with the these methods used, precision was achieved. H1 went with the original direct photon measurement, and achieved with that method 3% precision, and then finally decided to use Compton scattering for overall normalization, resulting in the final uncertainty on the luminosity normalization or luminosity value of 2.7%. So at the EIC, it will be much more difficult, and expectations are even higher. So since the precise cross-section measurements are really essential, it is expected that we measure the luminosity with precision better than 1%. And also very precisely determine the relative luminosity using the same method. The problem is that the event rates, for statistics reason, good news, are much higher than at HERA, but are so high that it becomes a severe problem also, because the event pileup scales also with this squared for ion beams. So in the most extreme case of electron gold collisions, we will see 10 gigahertz rate, so LHC type of rate of interactions. So nevertheless, this is what it is planned, what is planned to use the Bremsstrahlung. But then what we do? What about the beam size effect? Well, we argued that to somehow settle down the issue of this effect, we need to measure it more deeply, and for that we propose using van der Meer scans, so lateral scans of one beam against the other in transversally, and then measure the modifications to the spectra. And here you see what we have obtained, that if we compare with HERA at EAC in the medium conditions defined here, we see already suppression bigger than at HERA, whereas for the high energy case, they are even much bigger because they extend even to large energies. So this is the reason why we have to study it very carefully. And here is a surprising result we observed, that in contrast to the beam size effect, if we start to move one beam against the other transversally, we see amplification of the cross section. So what you see here is for the vertical beam displacement, we observed amplification of the cross section by a factor of 2 at effective one, of course, at low photon energies for displacement of the order of 4 sigma. So that definitely will give us a very good handle, not only to test the precision of the beam size effect prediction, but also study deeper this long-range phenomenon in Bremsstrahlung. So I will now quickly just flash the interaction region at IAC, which is being now planned, which made the provision for the luminosity measurements using Bremsstrahlung. I had to flip this drawing to show you, to remind you that to get the high luminosity at EIC, the collision has to be at large crossing angle to avoid spurious collisions, and not to lose then luminosity, the Crab crossing techniques is used. So basically it means that collisions are effectively head-on, and the vertex drift has negligible effect for the luminosity measurement because the large angular acceptance is being foreseen. So bottom line for this is that we need to instrument, because of yet harder or more challenging conditions at HERA to some extent, because of extremely high rate, this forward region in more detectors than even at HERA-2. And one of the main then challenges would be to minimize direct synchrotron radiation to avoid big energy uncertainties at the highest electron energy, and provide a very thin exit windows to minimize the event pileup effects in particular. We plan to use extensively the electron detectors also for the luminosity measurement itself, but they can be also used, of course, for tagging photoproduction, as was done at HERA. And here is just a reminder what it means. It is in principle converting the collider into the real photon-ion collider, because the typical virtualities of the photons in this type of reactions will be very, very small, as basically mass of the electron squared. the question, of course, is where it plays really the big role. Well, of course, from one point of view, this is obviously an advantage because, like for deep inelastic scattering, we use the scattered electron to reconstruct the kinematics. But as we shall see on the next slide, for some type of processes, this is not always necessary, but one should stress that nevertheless, for collisions with ion beams, this photoproduction tagging will become really very, very useful, and is maybe also worth noting that to make it, however, we need to have an extra instrumentation to avoid or to suppress enormous accidental coincidence due to the brainstorming process itself.
Krzysztof,
So
we are now.
Yes, this is my last slide. So
okay.
This is just my comment is that although for special class of events of fully exclusive photoproduction, detection of electron in principle is not mandatory, because the kinematics can be reconstructed from the scattered proton, but one should remember about semi-elastic cases and also for the two photon reactions where this can help also handling the semi-elastic contributions there too. So this is my summary. The precise luminosity determination is very challenging at the LHC, and in my opinion, two complementary methods are absolutely mandatory. I pointed out here in which case which one is strength is stronger, so to say, and new instrumentation is needed to get this precision at this challenging conditions. And finally, if we plan to tag photoproduction physics with forward detectors, we need to add extra instrumentation for electron detectors as well. Thank you.
Thank you very much for this really thorough talk on luminosity measurements and photo tagging at the EIC. This is a very important topic. Given that we are over time, I would at this moment say if there are any questions, please put them in the chat or contact the speaker directly. I would at this moment conclude the morning session, and so that we have about 8 minutes left for a short coffee break. And then we will continue at 10 a.m. Eastern time, that is then 4 p.m. Central European time, with the second session of the day. Thank you very much for all speakers. This was a very interesting morning session, and thank you everyone for participating, and particular for those who then also ask questions. Thank you very much.
Thank you.